One of our former presidents liked to play horseshoes. And what kind of motion is it when a horseshoe is thrown close to a pole? Simple motion or complicated motion? That's a lot of wobble. So, but does a horseshoe have a center of mass? Its motion would be simple, but where is the center of mass? Right there. Cannot support it. It'll be here. But there's nothing to hold on. There's no mass. But the center of mass is a concept of the mind. Sometimes that's part of the actual object, the actual body. Sometimes it's where nothing is. So for this one, I have a foil, and I've marked it with a red dot. And now when I support right here, that's where the center of mass is. I'll show later with the other method. So the other method, it'll be called the suspension method. That always works, and but it's a little bit more involved. The support method is simple, but it can only work when there's something to hold on. There's nothing to hold on here. So, but it has a center of mass, and when a horseshoe is thrown, besides all the wobble, there's one point that moves in a nice arc, parabola, and that is the center of mass. So hard to see because of the wobble and the distraction. We would have to put a lamp there, turn all the lights off, and then it would be a nice parabola. So this was motion through space, three-dimensional space. I want to look at a few examples where the motion is confined to the surface of the table. You see I'm wiping the table right now to make sure we don't have much friction on the table. I found a monkey wrench in my toolbox. Then I noticed it has a red dot on it. Huh. What could that be? Any idea? Maybe a center of mass? How could we find out? Support it? You're right. So that's the center of mass, that red dot, and I'm going to toss it across the tabletop now. It'll make noise, so be prepared for that. Okay? So I'll toss it so that it moves forward and also wobbles. So it'll be noisy. Okay, did you see? Wee. And so let's give that a rest. Do something else. I have this little puck. Going to toss that forward across the table, and how will that move? Also in a curvy line, or how? Straight line, because of what? Do I have here the I word? Inertia. Okay. So when we have no friction, then the true nature of motion shows up. There's a little bit of friction, that's why it came to rest here. If we polish more here, have an air track, it'll keep moving with the same speed and in a straight line. So, and now I'll show another picture that we took with the wrench when it was thrown on the tabletop. That's coming up now. So this is again a multiple exposure picture where a strobe light came on, flash, as the wrench was sliding across the table. And marked here with the red dot is the center of mass. What's your first impression? Quick. Complicated motion or simple motion? Complicated motion. It looks complicated. And so in my toolbox I found another tool besides the wrench, a pair of scissors. So I took that and cut the picture apart right along that line. So there you see, but it's not so easy to see because the wobble overwhelms the view. But the bottom is the same picture cut along the line through the center of mass, there you see it's a straight line. So the center of mass moves in a straight line. And if one would use a ruler from one dot to the next, to the next, to the next, to the next, how does that distance compare? Same or different? Quick. It's the same because the speed is the same. So the same speed. Also, that is not easy to see here. And so there's something very simple about the center of mass, this time confined to a plane. Then we see things move in a straight line. When we throw them through space, then we have the additional effect from gravity and get projectile motion parabola. So the conclusion so far is the center of mass is a very simple concept, but also a very powerful concept. Find for us the center of mass of this meter stick. Okay, so I see you use your finger and balance it on your finger, and it's right here, pretty much. It's not at the center of the stick. How come? So the center of the stick is at the stick is 1 meter long. How many centimeters is that? 1 meter has how many centimeters? 100. So half of the stick, the center of the stick would be at which mark? 50 centimeter mark. But this is at about the 34 centimeter mark. How come? Something wrong with that concept? It's not center of stick, center of mass, inertia mass. Okay, so what do we have here? The handle, that has inertia mass. So on this side, there's just as much inertia mass as on the other side. And that's why it's called the center of mass. Can you find out the center of mass of this stick? How would you go about it? Do you know?
I try to balance it.
You would try to balance it? Do you want to do it? Take it. Hold it up for us a little bit. Now, as you try to balance, you found something out. What was that? I could see in your face that expression of delight. You found that red dot. Okay, that helped. Right here. Okay, so it's not in the center of the stick either. How come? How can we explain that? It's the center of what? Of mass. There's a larger bulb on this side and a smaller bulb on this side. Therefore, it must be closer to the larger mass, center of mass. Can you find the center of mass of my pencil? Okay, you balanced it. It was about here. Okay, so that's not in the center of the pencil. It's more to the side. Why? Because of the eraser that has more mass to make up for it. I want you to find the center of mass of your own pencil right now. So this one has a cap on it, so you put your finger already closer to the cap.